Hello everybody, and welcome back to another episode of the Maybe Later Show. It's actually been a fairly reasonable amount of time between this video and the last, which is uncharacteristic for this channel, but very much appreciated. So, let's just dive right into it, shall we? So, let's say we want to compare two different things, apples and oranges, for instance. What are all the ways that we could go about doing this? Well, firstly, we could write two lists, one with all the pertinent qualities of apples, and one with all the pertinent qualities of oranges. As you can see from our list, apples are red, ready to eat, part of the rose family of plants. Fruits, very popular in the US, have a smooth texture and come in over 7,500 different varieties. Oranges, on the other hand, are orange, have to be peeled, part of the citrus family of plants, very popular in the US, have rough textures, are fruits, and come in over 400 varieties. With lists like this, it is very easy to see the differences between two things, but not so much the similarities, so maybe if we highlight them? But that just makes it look a little bit messy, doesn't it? And on top of that, we've accidentally made things just a little more inaccessible for colorblind people, or just people who are writing these lists on physical paper and don't happen to have highlighters on hand. So let's try something different then. Let's make a table. And honestly, this looks pretty good to me. If you're unfamiliar with how tables like this usually work, it could be a bit of an issue, but for the most part, this table does a pretty good job at comparing these two. The traits shared by both apples and oranges span both columns, while the traits that are unique stay in their respective columns. Just for the fun of it, let's add some more things to this table. And now we've run into the same problem we had with the lists. Despite the shared traits spanning columns, it's still hard to see what is similar between each of these plants. You might be thinking, wait a minute, they've just arranged these five specifically in a way so that nothing can align. But no, there is no possible way to get these five in an order so that all their similarities can span separate columns. Switching limes and broccoli means that we can get a much simpler table, sure, but the two sets that share the orange trait still aren't connected, nor are the two that share the smooth texture trait or the three that share the ready-to-eat trait. So how do we show that these traits are still shared then? We can either rely on the reader's ability to perfectly interpret the table, which is a simple task for this one, but gets much more difficult the more sets and traits there are. Or we can change the formatting in some way, through either colors, italicization, boldening, underlining, or changing the font. And now it's just as inaccessible as the lists were. It's still confusing to parse, and it just doesn't look very good. And, this group of apple, orange, lime, broccoli, carrot is not even that implausible of a group for someone to want to compare and contrast, so this is just kind of inconvenient. Overall, I would say that tables work better than lists did, but they're still not great. What's a better method for comparison then, if not lists or tables? There are things like T-charts, but those are really just lists in disguise. I'm sure you can figure out what I think is the best and most interesting method of visual comparison just by looking at the title of this video, the humble Venn diagram. For the most part, I would expect everybody watching this to be at least somewhat aware of what a Venn diagram is. You represent two sets with two overlapping circles, with the unique traits going into their respective set circle and the shared traits going into the overlap. They, of course, can get a whole lot more complicated than that. The runtime of this video should be an indicator for that fact. But for now, let's keep it simple and talk a little bit about John Venn. John Venn was an English logician and mathematician, and later on in life a historian and linguist, who is most well known for being the creator of the Venn diagram. There had been a trend going on in the 19th century math world of incorporating the ideas of logic into algebra. This was first made popular by another mathematician called George Boole, who himself is responsible for the system of Boolean algebra that interprets value through binary ones and zeros, and that modern technology would be lost without. Venn diagrams were introduced to the world in a paper written by John Venn and published in 1880, entitled On the Diagrammatic and Mechanical Representation of Propositions and Reasonings. He spends the first part of this paper going over Euler diagrams, more on them in a bit, and then proposes his new idea for visual set comparison with Venn diagrams going all the way up to the model for our 5 distinct sets. Why don't we take a look at those first 4 Venn diagrams that were proposed in the paper? But first, I would like to assign an exercise for the viewer. Venn diagrams with 2 or 3 sets are very simple to draw, but can you figure out how to draw one with 4 or 5? You can pause the video and go think for a while before coming back to the answer. I'll wait. Alright, so let's get into these. As expected, the first two Venn diagrams that are shown off here are pretty simple. The first is just the typical Venn diagram that we've come to know and love over the years, although he does accompany it with a system for writing out all of these comparisons. XY for neither X nor Y, the space outside the diagram. XY overline for not X but Y, the right circle. X overline Y for X but not Y, the left circle, and X overline Y overline for both X and Y, the space in the middle. The second diagram he presents is the same thing, but with a third overlapping circle for comparing three sets, labeled as such. After that, the diagrams get a little bit more difficult. Remember a paragraph and a half ago when I asked you to come up with a Venn diagram representing four sets? I would imagine many of you came up with a diagram looking like this. However, labeling each of these sections reveals an obvious problem with the diagram. The circles directly across from each other don't share any space. For instance, A and D share ABD and ACD, but there is no category for simply AD. And likewise, B and C share ABC and BCD, but there is no just BC. No matter how you draw this four-circle Venn diagram, there will always be some set that doesn't share a space with another. So, how did John Venn do it then? Well, let's take a look. But of course, the humble ellipse and some weird positioning allows us to make a Venn diagram where every set can overlap with every other set in every possible way. Logically then, you might be thinking that to create a Venn diagram to represent 5 sets, you would simply add another ellipse, and that's what John Venn thought too. But if you add it in the place you would expect it to make sense, you run into the same problem we did with the 4 Venn diagram. Venn's solution to this was just to cheat. He just put an oval right in the middle of it, so Z here is supposed to be that egg-like shape in the back, excluding the oval in the very center, which is only inside of Y and W. Venn writes that, "I do not think that any arrangement will much surpass the following," meaning that for Venn diagrams with 5 sets, this is as good as it's gonna get. But of course that's not true. I wouldn't have poured hours of my life into researching this if the best we could do was 4 sets in an exclusionary oval. There is a Venn diagram for 5 sets and far beyond that, but before I show you that, let's define some terms. So, what exactly is a Venn diagram? I know I kind of defined it earlier, but I definitely glossed over some things, so let's get a little bit more in depth. First, let's define what a Euler diagram is, because they share a lot of overlap with Venn diagrams. A Euler diagram must have all the following traits. 1. A Euler diagram must be made from simple closed curves. Simple, when referring to Euler and Venn diagrams, means that each intersection has 2 or fewer curves meeting at it. Closed just means that the curve has to fully loop back on itself, otherwise the part outside the diagram would spill inside the diagram. 2. A Euler diagram must have a finite number of intersections. This basically means that infinitely large Euler diagrams can exist. 3. A Euler diagram's intersections must all be transverse. If you don't know what that means, don't worry, it won't be super relevant to understanding this video. 4. A Euler diagram's curves must all be connected to the curve before it and the curve after it, besides the first and the last, which only need to connect to the second and penultimate, respectively. For example, the Olympics logo meets this requirement, because every ring connects to the ring after it and the ring before it, besides the first and the last. In fact, the Olympics logo meets all of the requirements for a Euler diagram. And then the special 5th requirement, which turns a Euler diagram into a Venn diagram, is that every possible combination of sets must be shown. The incorrect 4 Venn diagram we looked at before was a Euler diagram, but not a Venn diagram, because it was lacking AD and BC. The Olympics logo is also not a Venn diagram, because many of the rings never intersect. All Venn diagrams are Euler diagrams, but not every Euler diagram is a Venn diagram. Now that we have a proper definition for Venn diagram established, let's real quickly go through some of the terminology I made up for this video, which I think makes Venn diagrams easier to talk about. Firstly, I'll be shortening Venn diagram to Vennogram for the rest of this video, just because it's easier to say. Secondly, I've made a system of affixes derived from Greek and Latin designed to denote how many sets a Vennogram has, the rules for which should be on screen now. Theoretically, this would become a very inconvenient system at about 1,000 sets, but the highest we'll need to go in this video is like 17, so we should be good. Alright, so now let's talk about some other terms that are applied to Vennograms. A lot of these are just giving words to describe the properties we talked about already. A simple Vennogram is one in which two curves intersect at any vertex. Likewise, a non-simple Vennogram is one in which more than two curves intersect at any vertex. Most studies conducted on Vennograms are on simple Vennograms, and all the Vennograms I talk about in this video can be safely assumed to be simple unless I otherwise say so. K-regions are the parts within a Vennogram in which sets are compared. In the basic duo Vennogram, the section in the center is a 2 region because it is surrounded by two curves. The sections in the main circle parts are 1 regions because they are surrounded only by one curve. And the section outside the diagram is a 0 region because it isn't surrounded by any curves at all. Similar rules apply to the basic tri-Vennogram. A monotone Vennogram is one in which every K region that is greater than 0 but less than the number of sets, represented as n, borders a K-1 region and a K+1 region. A basic duo Vennogram is monotone because each of its 1 regions borders a 2 region. Similarly, a basic tri-Vennogram is monotone because each of its 1 regions borders a 2 region, and each of its 2 regions border both a 1 region and a 3 region. A reducible Vennogram is one in which any curve can be removed and it becomes an n-1 Vennogram. A tri-Vennogram is reducible because you can remove one curve and it becomes a duo Vennogram. The inverse property of reducibility is extendability, which means any curve can be added to form an n+1 Vennogram. A duo Vennogram is extendable because adding another curve forms a tri-Vennogram. And finally, let's talk about Winkler's conjecture, which says that every simple Vennogram can be extended by one curve to create the next simple Vennogram. This is true if the Vennograms don't have to be simple, and or if the Vennogram in question has 5 sets or fewer. However, because this conjecture isn't true for simple Vennograms with more than 5 sets, this conjecture is really only important for smaller Vennograms. And that's all the terminology, I think. Hopefully my explanation wasn't as confusing as the process of gathering all that info was. Explaining new concepts through a YouTube video is always very difficult because you're less teaching and more lecturing, so it's harder to verify how much your lecture makes sense. On screen now should be a simple reference section that you can come back to if you find you've forgotten what a term means. Now, let's get back to that pentavennogram from before, shall we? So, let's just take a look back at John Venn's original attempt at making a pentavennogram, just to refresh our memories. There it is. The problem here is that without that little exclusionary oval, this diagram violates the 5th requirement for a vennogram, and that with the exclusionary oval, it violates the 4th requirement for a vennogram. What then does a proper pentavennogram look like? Let's take a look at the trivennogram from before. Notice how triangular it looks? The specific type of triangle it resembles, an equilateral triangle, is a shape with rotational symmetry, which means that you can rotate it less than 360 degrees and the shape will appear the same. For example, this is what happens when I turn this vennogram 120 degrees from its original position. This is what happens when I turn it 240 degrees from its original position. And then 360 degrees brings us back to where we started. As you can see, it looks identical in many different positions, thus it has rotational symmetry. Now, let's take a look at a duovennogram. We can pretty easily superimpose a rectangle over this diagram, and a rectangle is yet another shape with rotational symmetry. Rotating it 180 degrees results in an identical looking image. Finally, let's look at a monovennogram, which is really just a circle. As you can probably imagine, circles also have rotational symmetry. In fact, no matter how many degrees you rotate a circle, it will always look the same. If we were to compare the n values between these 3 rotationally symmetric vennograms, 1 for a monovennogram, 2 for a duovennogram, and 3 for a trivennogram, we could make the observation that all 3 of these numbers are prime. So then, are all vennograms with a prime number of sets rotationally symmetric? To find out, let's try and rotate the quadrivennogram, which has 4 sets, not a prime number, and see if it looks identical before we've gone 360 degrees. As it turns out, the quadrivennogram is not rotationally symmetric, which makes sense. If you superimpose the most similar looking shape onto it, you'll find that it is this very not symmetric trapezoid. Of course, this doesn't confirm our theory that prime number vennograms are all rotationally symmetric. You can't confirm anything in math without lots of tediums and proofs. But let's try to make a pentavennogram in the shape of a star, which is a 5-pointed rotationally symmetric shape. And would you look at that, we've just discovered the pentavenogram, and it's simple and rotationally symmetric at that. Well, actually, we didn't discover this pentavenogram. This was actually discovered by Dr. Bronco Grunbaum in 1975 while he was working as a professor at the University of Washington. Grunbaum was actually a leading figure in Vennogram research for quite some time. He was also the person to figure out septavennograms, which are considerably more complicated. Research published later in 2002 and 2003 would prove that Vennograms can only be symmetric if they have a prime number of sets. However, once these first crazy-looking symmetric Vennograms were discovered, researchers quickly began searching for more. There's only one symmetric pentavenogram, but 33 separate symmetric septavennograms have been discovered. Logically, the next step was to find the Vennogram with 11 sets, the next prime number after 7. In 2002, Peter Hamburger published a paper entitled Doodles and Doilies, Non-Simple Symmetric Venn Diagrams, which detailed his discovery of the first symmetric decamonovenogram, which was very large and very non-simple. He did this using a method where you find one sector of a vennogram and then repeat and rotate until you end up with the full thing. Here is one such sector, and here is the full vennogram. This method of chaining sectors together was originally used in 1996 to find the monotone pentavenogram with the least number of vertices possible. To find the minimum number of vertices in any given vennogram, however, you must first know the maximum number of vertices, represented as v sub 1. The formula for the maximum number of vertices is relatively simple, 2 to the nth minus 2, with n representing the number of sets in the vennogram, as per usual. Once you know v sub 1, you can calculate the minimum number of vertices by dividing it by n minus 1 and taking the ceiling of that number. To just test our skills really quickly, we'll get back to the decamonovenogram in just a second, I promise. Let's try and figure out the maximum and minimum number of vertices in a vennogram with only one variant that we can easily check, such as a pentavenogram. First, to find v sub 1, we must raise 2 to the nth, which is 2 to the 5th, which is 32, and then subtract 2. 32 minus 2 is 30, so the maximum number of vertices a pentavenogram can have is 30. Dividing it by n minus 1, which is 4, gives us 7.5. Unfortunately, we've hit a roadblock. 7.5 is not cleanly divisible by 5. This means that we must round up to the next highest number that is divisible by 5, which in this case is 10. So the maximum numbers of vertices a pentavenogram can have is 30, and the minimum is 10. We can easily check this by simply counting. First, let's check that one that Grunbaum found earlier. 1, 2, 3, 4, 5, 30. You can count them all yourself if you'd like that reassurance, but I think I'm confident enough to say that Grunbaum's pentavenogram, the first symmetric pentavenogram, also happens to have the maximum amount of vertices a pentavenogram can have. That's not uncommon, however. Generally, the first vennogram discovered has the maximum number of vertices, and researchers have to work downwards until they reach the minimum, which they did. These vertices are already helpfully labeled for us, and we can easily verify that 1, 2, 3, 4, 10. This is the pentavenogram with the least number of vertices, or this is a pentavenogram with the least possible number of vertices. There are 5 other symmetric pentavenograms with only 10 vertices, and they all look roughly similar to this one. Anyways, Hamburger's use of the sector chaining method did not, as you can probably deduce just by looking at the diagram, produce the decamonovenogram with the least number of vertices possible, which is 209. He and some other researchers found one with 231 and then another with 220, but all of these were non-simple. Finally, in 2012, researchers Khaled Mamakani and Frank Ruski pulled off what seemed to be impossible and found the first documented simple symmetric decamonovenogram. Well, actually they found 200,000, but there was only one that made headlines and was published in STEM journals across the world, New Rose. This image definitely doesn't do it justice. To take in the wonder of the full thing, I would highly suggest visiting the website where these diagrams were first published, which is linked down in the description. Using the formula 2 to the nth minus 1, we can determine that this single image contains 2,047 distinct K-regions, each representing a different combination of all 11 sets. After this marvel of mathematics, the Vennogram trail runs a bit cold. It didn't take much longer for a very similar looking deca-trivenogram to be found, but that was back in 2014, and in the 10, now 11, years since then, I can't find much evidence that any more of these elusive, awe-inspiring Vennograms have been discovered. The next prime number still to be given a Vennogram is 17, and while it hasn't been found yet, as of me writing the script, I'll be sure to let everybody know once it has been. Overall, I would say Venn diagrams are pretty cool. I would have never expected such a niche, obscure topic to take hold of my life as combinatorics, but here we are at the end of the video, all about them. As always, everything should be down in the description. This was the first video I've made on this channel where it felt like I was foraying into uncomfortable territory. I am not a math person, but I've learned a lot along the way, and I hope you have too. Anyway, that's all for me today. I've been Alivelâ, and I still don't know what polar symmetry is.